If you've watched my last two videos, you've seen that we have a basic framework for monsters. The problem is we're not doing a whole lot with it yet. In this video, I'm going to be laying out some of the systems used by the game's monster AI, and then I'll start breathing life into the first handful of dungeon denizens. I'm assuming if you've ever played any video game made in the past 4 decades, you probably have some base level understanding of what entities are. To save ourselves some time, I'll just say that entities are objects in a program like NPCs, trapped items, projectiles, and particle effects. The monsters of Ashes class are represented as a subtype of entity called mobs, or mobile objects. All monsters in Ashes class are built off of a base class of dubbed entity mob and contain a number of universal variables, like the current floor they're attached to, their coordinates in the current floor, their stat dice determining how much health and mana they can spawn with, their current health and mana values along with the max values for both stats, their hunger, which determines how fast the monster can regen health and mana, if at all, the monster name and species type, their leader, an optional variable for monsters that allow them to behave with more unit cohesion, the movement type, and the movement speed. Some of these variables are set when designing a mob and are never changed in-game, but others are specific to each given mob in a dungeon and will constantly change throughout the mob's life. The entity mob class also contains a few functions that are used to run the monster's AI code, those being move and move delta, which are used to adjust the monster's coordinates. Do heartbeat, which runs a number of universal actions for all monsters, like dying, regaining health, and what have you. Checkers to see if there's a valid movement phase for a mob and if the mob can step on a given position in the dungeon. And Do AI, a currently empty function that executes the monster's specific code. All mobs in the game inherit the bulk of their code from this base class, and will override the Do AI function with their own unique behavior patterns. It seems really barebone, but structuring our mob code this way gives us all the flexibility needed to make mobs do essentially anything we want them to. For a very basic example, here's the code for the mouse entity I built in the second Bytes video. Not a whole lot going on, but what it's meant to do, it does well enough. Before we get into mob AI, there are 2 important things I need to elaborate on, and those are the speed and movement type variables. Okay, so in a lot of roguelikes, gameplay is handled on a turn-based system. However, some monsters in these games will move faster and slower than others, which means you can't just have each entity update on each turn. Similarly, some spells and items will speed up or slow down an entity, meaning we have to factor in variable speeds for entities. In Powder, there's 4 speed phases: slow, normal, quick, and fast. The underlying system behind these phases is super confusing, but here's the best explanation I could come up with. The game runs a 5-step counter that goes through the phases in this order. When an entity is updated depends on what its speed is. If an entity is slow, it will only move when the counter hits normal, meaning for every 5 steps it gets 2 updates. If an entity is normal, it will move whenever the counter is set on normal or slow step, meaning for every 5 steps it gets 3 updates. If an entity is fast, it will move whenever the counter is set on normal, slow, or fast. However, it will not move on the quick step. Similarly, if an entity is quick, it will update on all steps except for fast. This can lead to some interesting interactions when fighting a fast monster when you have the quick attribute, as you'll both have a step where you can act but the other party can't. Now, how the modifiers slot into things goes like this. If an entity is given the quick or fast modifier, they get an update on those respective steps. So if you're in normal base speed, getting zapped by one of these modifiers gives you a 33% speed boost. At fastest, an entity can move at 167% speed, meaning they're moving on every single step in the global phase counter. Note that quickness isn't a natural speed monsters can have, rather it's a buff that's granted from using equipment, magic, or by eating certain monsters. If an entity is given the slow modifier though, they instead lose a heartbeat step during the slow step, meaning they're moving at 67% speed compared to a normal entity. It's sort of difficult to explain using words alone, so let me just show an example here. Here I've spawned 5 generic monsters, one slow, one normal, one fast, one quick, and one that's both quick and fast. As you can see, monsters that have either a fast or quick movement type get the same speed boost but at different points in the speed counter. So why do it this way? Honestly, it's just a lot cleaner in practice. Since we're operating on a 2D grid, most of our movement calculations are going to be done as whole numbers. And also using stuff like a float for the speed doesn't really work out well when it's a turn-based system. So here we have a few monsters in the various terrain types you'll see in Ashes Quest: flat ground, fluid tiles, and solid obstructions. One approach that works fine in most games is to simply check if the tile is solid or not, and allow the mob to walk based on that. But the problem is this isn't really realistic in roguelikes, and we want to prevent some monsters from crossing over certain tiles for either logical or flavorful reasons. When it comes to fluid tiles especially, we don't want to just allow anyone to walk over water without any consequences. Well, unless they have the boots of water walking, that is. So how do we implement this? Do we just add a second boolean for whether a tile is fluid? Nah, there's a better solution for that. Instead, we give each tile a variable for its movement type, represented as an integer. The number may seem random, but what we care about is their binary values, which we can use as a more condensed array of booleans. These first 6 values serve as the movement type for the tile definitions, while these remaining 4 are used for monsters to see what tiles they can move across. When a monster checks to see if it can move onto a given tile, we do a bitwise AND operation with that and the monster's movement type. If the result isn't 0, we know we can safely pass through. This means that normal monsters like rats and kobolds can only cross flat surfaces like the room and cave floors. Flying monsters like bats and dragons can fly over fluid tiles, and incorporeal or phasing monsters like ghosts can pass through solid objects. Note that we don't allow ghosts to cross over fluid tiles, and this is due to various pieces of folklore that describe spirits as being unable to cross bodies of water. We can also give some monsters the ability to only pass through fluid tiles in case you want to add any aquatic fauna to the game. So now that you understand a bit more about how movement works with these last 2 systems, let's get all Frankenstein up in this bitch and work on the monster AI. So in the second Bytes video, we implemented a basic pathfinding system for mice. That was so Q2 2024, and we're in the future, so let's add more monsters and tinker with their AI. So full disclosure, this is my first time writing an AI system more complex than Boyd's flocking program. I have no idea if my approach will be ideal or optimal, but I think that makes it more interesting for you guys since we're all starting with the same knowledge on this front. The idea I've got right now is to create a series of functions for the AI tasks, such as moving, attacking, zapping wands, and other shit. These tasks will be called by the mob's doAI function in their class file. I do know Powder uses an approach similar to this, but instead using a single doAI function for all mobs. Now since I'm setting up the contents of the doAI function for each mob class, we do wind up using more disk space, but in the process we wind up reducing the overall execution time for the AI step of the game loop. First things first, let's just add a basic wandering task. This is super easy, as we just need to pick a random directions the monster can move towards and have them do so. And already these guys are looking pretty lively. But to add a bit of extra variety, we'll give them a 25% chance to just wait and skip that movement opportunity. They could just take a moment to stretch, drink some water, and make sure their eyebrow game is on fleek. This next task is new to Ash's quest, which is hunting mode. See, the idea I had was larger predatory mobs, so I should go out and start searching for weaker monsters to chow down on, if their hunger starts dipping below a certain point. This can actually lead to some interesting gameplay if you wind up lingering in a dungeon for too long, or repeatedly backtrack to previous levels, as more dangerous monsters will start picking off the weaker ones. For this, we cycle through the list of dungeon mobs, and look for something that's nearby, within direct line of sight, and has less health than the monsters entering hunt mode. But that has 2 immediate issues that can make this look a bit silly. Since we're storing our monsters in an array list, right now the hunter will prioritize the first mob in the list that has line of sight with, which could lead to weird scenarios where it will ignore a monster right next to it and pick a monster 7 tiles away simply because it spawned in first. The second issue is there could be fresh kills in the immediate vicinity that are either left by the player or another monster. Wait, shit, I don't have drop items yet. Okay, now I have dropped items. We'll go into more detail on that next episode, so don't worry. So before we start eyeballing our roommates' potential meals on wheels, we're going to cycle through the floor's entity items list and see if there's any corpses in view that we can munch on. If there is, exit the loop and set priority to that corpse. If there isn't any delicious floor meat, then we cycle through the entity mob list, checking to see if each monster is in line of sight. If it is and its health is less than the hunter's, we note the distance between the hunter and the prey. If the prey candidate we're checking is closer than the previous closest candidate, we set that prey as the new ideal candidate. Once we've gone through all the monsters in the list, we set the closest monster we've seen as our target. Congratulations, you poor little miscreant. We would like to offer you an official position as lunch. You cannot refuse. If a monster has a target, it will proceed to move in the direction of that target. To do that, we get the X and Z direction between the target and the hunting monster, then normalize these distances to a range between -1 and 1. If both distances are non-zero, then the monster will move along the axis with the greater distance. In the case of corpses, once the monster reaches the target, it'll simply eat it. Note that we're also storing a 2D vector for the target's last known coordinates, and updating it at the beginning of this routine if we have direct line of sight. If we lose line of sight of the target and either reach the last known position without regaining sight of it, or are no longer able to follow it, we will instead load their smell trail and attempt to follow it if possible. But what happens if there's an impassable barrier between us and our target, but we're smart enough to identify a way around said obstacle? In this room, there's a dummy target and 3 monsters, a zombie, a slug, and a kobold. Separating the dummy and these monsters is a moat. Having no higher brain functions or self-preservation, the zombie immediately walks into the moat where it sinks and dies. The slug realizes it can't swim and avoids the water, but since it sees the dummy, it paces along the edge of the moat, attempting to find a way to cross. The kobold realizes it can't cross the moat, but unlike the slug, it sees there's a corridor behind the dummy. A corridor that just so happens to connect to his side of the moat. This is where you start getting into more complex pathfinding. How do we get the kobold from point A to point B? Fortunately, there's a ton of algorithms that are both fast and easy to implement, chief among them being the A-star search algorithm. The way A-star works is it propagates through the level, creating nodes through each tile. We incorporate our movement type system by checking if the tile the node will be placed on is traversable by the monster we want to use, skipping any tiles that are impassable. Once the algorithm finds a path to the destination file, it passes it along to the monster, and the monster will instead prioritize the path it's been given. Naturally, we don't want to give every mob this ability, as this can increase the difficulty to unfair levels. But you know, we have corpses in the dungeon now. And I mean, if they're there... So this is one of those ideas where I'm not really sure if it will make its way into the final game. I haven't really tested it for gameplay balance at all. But one of the mobs I'm bringing over is the Lich, which is an undead spellcaster found in crypts and later levels of the dungeon. In Powder, these guys have access to 6 spells, but none of them were actually Necromancy related. So as an AI task, I'm going to be giving Liches the ability to create zombies from corpses. To start this off, I'm going to be adding a variable for them that tracks how many undead they currently have, just so we don't wind up with a Walking Dead horde. If the Lich has no higher priorities and has less than 3 familiars, it will run a check to see if there's any corpses nearby as it wanders the dungeon. Once it has its eyes on one, it will converge on that corpse's location, and once it's within 1 tile of the corpse, it'll turn it into a new zombie. Now, I'm making this task separate from the actual Raise Undead spell, for one because I don't actually have the spell system fully implemented yet, and for another, Raise Undead doesn't have a limit to range, so as long as the corpse is in line of sight, you could raise a zombie. I'm sure you could imagine how dangerous that could get. This is another unique AI task I'm doing because I think it'll be kinda neat and I want to showcase how much more control we have over monster behavior. If a dragon finds an item made of gold, it'll pick it up and look for a place to build a nest. The conditions for a nest is any solid rock tile that has 5 or more solid neighbors. Once it's found a spot that meets this condition, it'll burrow into that wall and create a hoard spot, depositing the item it found at that location. It'll then make a note of the location of its hoard and how many items are there before it continues on its way. If the dragon returns to its hoard and finds something has been taken, it'll look for a nearby smell trail and attempt to hunt down the thief. I've added a check for the dragon behavior so it'll ignore items that are in hoard tiles unless the owner of the hoard is dead. This is solvable just by adding a list to the floor class that tracks these locations and who their owners are, and deleting the hoard from the list if its owner is dead. So we have a few tasks ready to go, but we need to flesh out the behavior to really make sure everything is working as intended. To do that, we're creating a second behavior category called Actions. Let's go over a few important ones. This is the default action for moving in a given direction. We double check to see if we can step into a new tile by checking if there's any monsters currently occupying it. If we can't, we check what our disposition is towards the monster. If we're neutral towards it, we cancel the movement. If we're friendly towards it, or if we're ambivalent towards it and have a path we're following via smell trail or a star route, we push it out of the way by swapping places with it. If we're hostile towards it, it's the action for walking, nothing really to write home about. This is the actual swapping action. Mobs controlled by the player are generally only going to be the ones calling it directly, but we run some additional checks here to make sure that both monsters engaged in the swap can move through the tile that the other mob is standing on. So this stops a flying mob from swapping places with the rat and dropping it into a pool of lava and other edge cases like that. Similarly, we make sure that the familiars and summons can't initiate a swap with their master. After all, it doesn't really make sense if a monster can push around its creator. If a monster bumps into something that is hostile towards, it'll attack it. First thing this does is it sets the defending monster's target to the attacker, since even if no damage is dealt, the intent was there. There's a huge amount of logic that goes down with this action, and it requires both intrinsics and items, two things I haven't really covered yet. And while I can just write these systems into the engine, in fact the intrinsic system is how we have mobs moving at different speeds, I want to be able to actually explain what's going on under the hood, so I'll put a pin in the more detailed explanation for later. For right now, all we need to understand is each mob can perform a given attack based on die rolls, since we use a more D&D-centric attack system where damage can vary rather than a more common system of a sword doing 5 damage or a Glock doing 12 damage. Beyond that, we use a D20 roll to determine if the attack actually hits or not, ranging from a 1 being a critical failure to 20 being a critical hit. We'll be going back to this in a future episode because the bulk of the differences rely on weapons being used and skills had by both the attacker and the blocker. So to test things out, I'm going to drop a bunch of random mobs in a room with a starving dragon and whatever happens, happens. Alright, looks like the combat's working. This whole video is the result of a lot of hard work, research, and cursing out my computer. So if you liked what you saw, consider giving me a like and subscribe to my channel if you want to see what comes up next with the game engine. It's free and it lets me know you guys are enjoying the content I've been putting out so far. If you want to further support the game, you can check out the description for my Patreon, or I've provided a downloadable test build for you guys to mess around with for paid patrons. Source code will be included, but you could also just farm flower to take apart the jar file. Anyways, that's all for me, and until next time, thank you guys so much for watching, and I'll see all of you in the next one.